you can solve. We are now going into, let's say, the deep waters of fuel cell technology. We're walking through components, stacks, and we're scratching a little bit systems if time will allow. So first, we're talking about components. Like the components we use in a fuel cell. Basically the catalyst, you learned a lot about that this morning, just brief reminder to that, the polymer electrolyte, and then we will have some aspects of water management in there. So a reminder from yesterday, just fuel cells are made of components. However, the components themselves can be thought of being decomposed into functional layers. And so we've got that one, which is the electrolyte passing ions, blocking electrons, the anode making protons, generating electrons, and the cathode, in a sense, sinking electrons and sinking protons, making water. We've got the gas diffusion media, which are in charge of, let's say, equally distributing the reactants. And last but not least, there we have the gas distribution layer, which is in charge of, let's say, providing flow to all square micrometer, nanometer, picometer of the fuel cell. And then we have the current collectors. We have typically something like a thermal management part, and then it repeats over and over again in the stack. So what do we need to make a fuel cell work? Let's start from the left. We need a negative electrode. We call it the anode. Why do we call it the anode? Any idea? It's a convention, that's right. And what does the convention say? Right. It's that electrode where things are oxidized. Right. So in the negative electrode, we need to transport hydrogen to the reaction sites. We need to catalytically oxidize the hydrogen to protons. We have to collect and to conduct the electrons, and we have to conduct protons and move them to the electrolyte. And to a certain extent, we also have to manage a little bit of water movement in the porous structure of the anode. In the electrolyte, in a sense, we have to transport the protons at a rather high rate. The higher the better. We have to stop the electrons, and we have to separate the reactants, oxygen from hydrogen and vice versa, as good as possible or as good as reasonable. It's always a compromise, you know. If it's too good, well, fine for the electrolyte, but maybe bad for something else. If it's too bad, so bad for the electrolyte. And in the positive electrode, the cathode, we need to transport, obviously, oxygen to the reaction site. We want to catalytically reduce it and react it with the protons from water present in the fuel cell. We need to conduct and supply electrons, and we need to conduct protons and supply them for oxygen reduction. And obviously, there's lots of other stuff to supply and distribute reactants, collect current, manage heat, water, but focusing on a cell, on, let's say, one dimension of a cell, that's part of another story. So what do we need in terms of catalysts? We need high activity to sustain the hydrogen oxidation, and on the other side, the oxygen reduction. You've learned from the lecture given by Claude Lamy that we typically use nanoparticles. Catalyst science always was nanoscience. Nobody talked about that until that term came up. And nanoscience was all of a sudden was hip, and catalyst science was boring. In any case, catalysts are nanoparticles, and we have to worry about all that nano issues that people gradually realize are valid for other nanoparticles as well. So we need to have these particles resistant to growth in order to provide sufficient active surface area. Therefore, we use supported catalysts. And since the catalyst itself, we think of it as platinum. It's very well electron conducting. However, if we want to use it as a catalyst, as an electrocatalyst, we need the support also to be electronically conductive. And we need all that stuff, support, catalyst, and so on, resistant to the electrolyte. And that's one of the reasons why many materials which are pretty good hydrogen oxidation catalysts or oxygen reduction catalysts are out of scope for PEM fuel cells, since the PEM fuel cells are typically based on an acid electrolyte. And so there is little which is resistant to acid electrolytes at the potentials you find in a fuel cell. It also has to be resistant to the reactive environment. Remember, at the anode we've got hydrogen present, we've got water present, and we've got protons present. And the cathode, we've got protons present, we've got oxygen present, we've got water present. So this is a challenge to any material, and if you ask a materials engineer which materials are good for, let's say, being in contact with highly pure water, or being in contact with acid, or being in contact with steam, the selection is pretty narrow. The gas diffusion layers, they're in charge of microscopically distributing the reactants, collect the current, and be part of the water management. They need to be obviously highly electronically conductive. They should show a very, very low interface resistance. They're normally made out of a bilayer structure from a fiber substrate with what we call a microporous layer covered. They are wet-proofed in order to stay open for gas transport. It doesn't make a lot of sense to waterboard a fuel cell. You know the principle of waterboarding. You get a cloth across your mouth and they pour water on it. So try to breathe. Pretty much the same for a ground fuel cell. Waterboarding a fuel cell is no good, right? So we need to keep the gas pores open, but we also need to leave room for liquid water. That's also important. Liquid water will be present in the fuel cell, and we need it somehow to keep the electrolyte conductive. Then finally, the electrolyte, it needs to be ion transporting, high ionic conductivity, mechanically and chemically stable, right? Mechanically stable sounds like strange, but it's a very, very thin layer, 25 microns, and it must support a lot of mechanical force up to 10 bar. So it should be mechanically stable. It should be resistant to pinhole formation, and so on, and it should be insensitive to the environmental conditions, like having more or less water. How good that can be fulfilled, we will see. And then finally, behind the gas diffusion layer, we find the bipolar plates to collect current, to macroscopically distribute the reactants, to be part of the heat management, and they need to be highly conductive, they need to be corrosion resistant, they should prevent the mixing of the reactants from the backside, and they should provide access to the thermal management. And finally, a frequently forgotten part of the fuel cell, the seals. You have to somehow seal hydrogen in, or oxygen or air in, and leave it there without having oxygen or hydrogen leaving the fuel cell. So, well, then we are back to square one. Fuel cells are electrochemical reactors, which spatially run separated electrochemical reactions, hydrogen and oxygen, into water, electricity, and heat.
And those seals, I guess, should be diffusion free, right?
Pardon me?
Those seals.
They should minimize diffusion, right?
And there is no such material.
Well, there are a few materials, but it's a tough cookie. It's there's a saying in engineering that nothing is leak proof.
That's right.
So you have to live with a little bit of hydrogen going all over the place. And let's say the most leaky part, hydrogen-wise, is the electrolyte membrane. It's also, other things coming in you can prevent pretty well. But in terms of hydrogen going out, the most leaky part is the electrolyte membrane. It's also the largest area where hydrogen faces another medium. So, in a sense, the electrochemically active processes, they are taking place at a catalytic active surface, and well, the detailed mechanism of these electrocatalytic processes frequently involves several steps. So the catalyst itself, just repeating what Claude said, is demanding. It needs a high activity for reaction. It needs to provide a large surface area. It typically appears like small spherical particles, but looking closely to them, they are more or less truncated octahedra, which by themselves show different surfaces to the outside. They should be resistant to poisoning. You learned the issue about carbon monoxide. They should retain their surface. They should not degrade. They should be inexpensive. They should be whatsoever. And well, these catalysts, they have to enable reactions, and the apparently very simple, and as we have seen from the experimental data, very reversible and fast hydrogen oxidation reaction by itself is a multi-step process. So hydrogen has to come somehow to the surface. It has to somehow interact with the surface. It will dissociate, and then it will release electrons and move as a proton into the electrolyte, and we call that the Tafel-Formel mechanism of hydrogen oxidation. But you can easily disturb that two-step mechanism by just messing up the surface with carbon monoxide, with sulfur, with everything else that bonds more strongly to the catalytic surface. You can always think of a catalyst as a go-between. So it arranges a marriage, but it doesn't take part in it, right? So, as we learned, pushing electrons through an interface means that the reaction rate is, so to speak, depending on the material, on the electrolyte, on temperature, on pressure, and on the potential of this electrode. And you remember the exchange current density. It is a measure of the rate of reaction to a certain extent. Here, it's a measure of the activation enthalpy, and it also involves something like the reactant concentration to a certain extent. And so, from that point of view, if we want to influence the exchange current density, the rate of overall reaction, we have to somehow do something either about the rate constant or about the activation enthalpy. And as Claude mentioned, several catalytic materials are, in a sense, shifting this activation barrier. And no catalyst will remove the activation barrier, obviously, but it will shift it to a way that more particles can reach the transition state, and so it provides, in a sense, a tunnel through the original activation barrier. And now we can, let's say, measure the exchange current density of different materials, starting from mercury, ending in lead, going through gold and platinum, and you see that there are orders of magnitude in between the exchange current density for hydrogen oxidation reduction on mercury, on platinum, on lead. So there's something to those surfaces, and we can describe that, and we can, in a sense, correlate that to some other physical properties, for example, like the enthalpy of evaporation of metals, and then we can make these wonderful volcano plots where there is something at the top, and where some of the materials favor adsorption of the, let's say, of the materials. Some of them are not desorptive enough, and so the best catalysts are providing the best compromises. Now, these more empirical relations, these more empirical volcano plots that you can correlate with, let's say, heat of evaporation, with many other things, bond strength, and so on. Meanwhile, you can do a lot of computational chemistry on these materials, predicting properties like volcano plots for, let's say, more exotic materials rather than simply the metals which you can find in the periodic table. Again, in the hydrogen oxidation reaction, kinetics are fast when using platinum catalysts. They are typically, we can live with very low platinum loading if we have very pure reactants. At the moment, we have little economic interest to replace platinum when using pure hydrogen as a fuel. We have more interest in replacing maybe platinum on the cathode side, since we need more of that at the cathode. And we have that two-step mechanism, the Tafel-Former mechanism of oxidizing hydrogen into protons. Now, is a platinum catalyst a good choice? Well, it's sensitive to CO and sensitive to almost everything else. However, if we want to benefit from the fast hydrogen reaction, we have to make sure the surface is free. And from that point of view, we have to rely on very, very pure fuel, and we have to remove some impurities from the fuel pretty thoroughly. And this is particularly carbon monoxide, sulfuric dioxide, hydrogen sulfide, sulfur dioxide, sulfur trioxide, to a certain extent ammonia. So, well, we face a challenge in terms of running a fuel cell on a platinum catalyst. And if we don't do, we block the surface, and in a sense, we stop the first part of this oxidation mechanism of hydrogen. Now, in case of CO, we can, let's say, mitigate the effects by alloy catalysts. Claude was telling about that. We can mitigate the effect by raising the temperature. So we have, in a sense, ways of handling the overall issue, but be aware, minimizing the platinum load to the theoretical minimum will not not end up in a working fuel cell. How about oxygen reduction? Well, we have most of the losses that we find in fuel cells are based on the oxygen reduction, and this is just a graph which processes are involved in oxygen reduction, and I don't want to go into details. So that's where we want to end. But the road to that where we want to end is pretty much blocked by some species which are to a certain extent strongly absorbed. And strongly absorbed means always low free area for new reactants, right? And we have a side path to oxygen reduction, which is what we call the 2-electron reduction, where we don't go into water as a product, but we end up with hydrogen peroxide as a product. So we have less current efficiency in that respect. We need more oxygen to be reduced at that point. And the second issue is hydrogen peroxide in the presence of organic materials is somehow aggressive, and well, we face trouble with hydrogen peroxide when running any kind of electrolyte membrane. Then there is, pardon me? Right. Then there is one more thing. Even if we want to measure the reversible oxygen potential in a fuel cell or on a platinum surface, if we have a freshly polished, freshly tempered platinum surface, and we stick it into an electrolyte, then we will see for a split of a second the reversible oxygen potential, and then it degrades. And the reason is that the surface of platinum at the oxygen potential is not inert. It interacts with oxygen, with water from the outside, and it forms some more or less ill-defined oxide hydroxide type surface, which in a sense forms a mixed potential between oxygen, platinum, and the platinum oxide phases. So we have the first thing of a mixed potential formation right at the beginning of the fuel cell.
So the fuel needs to be always on, perhaps. Right?
No.
You cannot turn it on and
No,
off.
no. It happens if you go to open circuit potential. So if you add fuel to such a surface, it will reduce. You will the surface oxide will decompose and will go down. And if you have seen Claude's nice cyclic voltammograms, there is that bump, that anodic bump at the high potentials. Then it goes to oxygen evolution, and there is a cathodic bump at some lower potential, somewhere around 700 millivolts versus hydrogen, where these surface oxides are reduced.
So what's the problem if hydrogen cleans the surface off again?
Well, it's not a problem for hydrogen, it's a problem for oxygen. Okay, so the two ways of oxygen reduction, just keep them in mind, they will happen. And we will find preferred formation of peroxide at low potentials, and this has an implication for oxygen penetrating through the electrolyte membrane to the anode. There it is low potential, there it will be reduced, there it will form a significant amount of peroxide. We also have an issue, we can't cover it in this lecture series completely. If fuel cells degrade, platinum is dissolved from the cathode, is moving into the electrolyte, and as the potential drops, there's a band of platinum forming in the electrolyte membrane. And at this band of platinum, hydrogen and oxygen meet, and so they are reduced. And since hydrogen is more mobile than oxygen, it will have low potential and it will form peroxide. So essentially what we're doing, we are making tiny little nanoparticles of noble metals, sometimes noble metal alloys, as we learned that they are to a certain extent more active or more robust than the pure platinum. We support them on a conductive support. Typically we support them on a carbon base, and then we integrate them into a couple of micrometer thick layer on top of the electrolyte. We have the electrolyte, and the other side it goes right back. Now there is a certain limit to minimizing the particle size. These nanoparticles tend to agglomerate, and particularly they tend to agglomerate if they can move freely on the support surface. Therefore the support needs to be porous, that they get trapped into the pore. The pores need to be wide enough for the reactants to get in, for the water to get out. But you see, if you just plot, let's say, the surface area of spheres with decreasing diameter, then you see the surface area at a certain point almost increases infinitely. But be aware, this is about 5 nanometers. That's the size limit where our assumption, well, these are spherical particles, needs to be revisited, and the real structure of these now some 2,000 atoms big macromolecules, which we call platinum nanoparticles, needs to be taken into account.
In colloid science, what we learn, those nanoparticles are affected if they are separated.
Yeah.
You produce a nanoparticle, you leave it there, they get together, become big particles.
Right.
You no longer have the effect of nanoparticles.
Right.
When you put those nanoparticles on the membrane, isn't that they become?
That's the reason why we support those nanoparticles on the surface of porous carbon, in order for them not to find their way to each other.
They're around it.
They're somehow in the pits of a golf ball or whatsoever.
Like a composite.
Right.
In a matrix.
Right. You can see those. Those are nanoparticles surrounded by the carbon. So the polymer electrolyte membranes, we've got about, for the low temperature PEM fuel cells, about 3 different kinds. One that's fluorine free, one that's partially fluorinated, one that's to a certain extent perfluorinated, and I will leave out all these beautiful composite membranes based on polybenzimidazole and phosphoric acid, since that would take forever in the day if we covered these here as well. So, oops, that was one explanation why we are using supported catalysts. So the noble metal nanoparticles tend to agglomerate to larger particles, and these support structures are carbon blacks. They're highly conductive, they have a high flexibility in pore design, but they are susceptible to corrosion at high potentials. Always remember, carbon is thermodynamically not stable at the potential of the fuel cell cathode. It might be thermodynamically almost stable at the potential of the fuel cell anode, but at the potential of about 200 millivolts versus hydrogen, carbon starts to become unstable and carbon starts to corrode into CO2.
What kind of carbon do you use?
These are typical carbon blacks, let's say sort of medium to high surface area carbon, which are either furnace blacks or which are other ways of carbon blacks.
For example, glacial carbonate, Vulcan XT72, you know?
Yeah.
What's the difference between them?
Well, the difference between one could have a summer school on carbon, like a summer school on fuel cells, and you would never get an end to that story. Basically, the microstructure is different, the wettability is different. You have different terminal groups at the carbons, depending on the surface treatment, and depending on, let's say, the growth conditions of the carbon blacks. And so there is dozens of sorts of carbon black available, which you can use as catalyst support or not. And let's say there is a general rule of thumb that the higher the surface area, the better the initial performance, the worse the endurance. So carbon blacks are highly defect structures, and from that point of view, they are very susceptible to degradation.
What about the nanocarbon tubes or graphene? There is work done using these as support. The carbon nanotubes, they typically don't have the high surface area that we need, and they have pretty smooth surfaces, so they don't prevent the carbon from sticking to each other or moving towards each other. However, they are providing better conductivity. So there's a lot of work done recently on mixing classically supported carbons with these carbon nanostructures. On graphenes, let's say, I'm not aware of too many investigations using graphene type materials in the as catalyst supports for fuel cells. So let's have a look into the electrolyte. Now, electrolyte means ion in motion. But these electrolytes we're talking about, they're basically somehow aqueous electrolytes. So the ion that's in motion is surrounded by what we call a solvation shell. It's pretty much like a teenie, like a rock star walking through a group of teenies. You know, they're screaming and they're trying to get to that person, and gradually he is moving along, and some teenies fall back, some new ones get attached to it. So that's about the same situation as an ion that's moving through an aqueous electrolyte. It has a group of followers. We call them inner solvation shell, secondary solvation shell, ternary solvation shell, depending on the radius and on the charge of the ions, how big these or how wide these extend.
The first one looks like body bags.
To a certain extent, well,
Change after
they are in a sense they're in a sense more closer related, but they're also changing.
More structured, yeah.
Right. You can do some model calculation, some molecular mechanics calculation where you can see, let's say, a pore filled with an aqueous solution of sodium chloride, and if you extract the water, then you see the chloride ions, the sodium ions. So they're pretty close to each other in a concentrated solution, but they're still separated by that water, and it's, as you can imagine, moving through that crowd of water is not all that easy. Now, if we look at the conductivity of materials like containing protons, like containing OH minuses, like containing potassium or barium or chloride, then we see that the protons and the OH minuses, they stick out from the overall conductivity. So there must be a reason to that. In a sense, we have to wonder why on earth do these constituents of water stick out of the ordinary conductivity values that we find for ionic for ions in solution, and why in a sense this extra conductivity vanishes at about 150 degrees. And in that case we have to be aware of that water, H2O, in liquid state is not H2O. It's an agglomerate of at least 4 to 8 molecules, so it's something like H8O4 or H.
Ice-like structure.
Yeah, something. It's not ice-like. It's some clustering, and then you can imagine that this cluster, for example, this water cluster, if a proton approaches here, these water molecules, they don't stand still. They're vibrating. They're doing all kinds of nasty stuff. And these chemical bonds we are talking about are, well, nothing more than, let's say, probability functions of electrons of electrons around here. So when this molecule is vibrating, it can, in a sense, happen that some of these, what we draw as chemical bonds with the solid lines, just switch from here to there, here to there, and all of a sudden the proton, without physically moving, is released at the other end of the cluster. It's basically a rearrangement of hydrogen bonds. And from that point of view, you don't need to a dissolved salt needs to physically move. These protons don't need to physically move to be transported. They just need to rearrange their, let's say, solvation shell, and that means, in a sense, since rearrangement of solvation shell takes, let's say, part in 10 to the minus 12 seconds rather than milliseconds, like moving protons or moving ions, this will, in a sense, lead to much faster ion conduction in protonic solvations.
Sorry.
Yeah.
This is different from what?
This is basically the Grotius mechanism. Yeah. Rearrange. It's called the Grotius mechanism, and you can do a lot of let's say individual stages and define the Sundel ions and the eigenions and ions and all that stuff. But in a sense, from a, let's say, a more helicopter view or a point of view, it is a rearrangement of chemical bonds via vibration, right? It's yeah. In the polymer electrolyte membranes we are talking about today, it's like in the aqueous. It's no small polaron hopping. It's the small polaron hopping is involved as well, but let's say the extra speed that these protons or OH minuses are picking up, this is due to the Grotius mechanism, and this is not due to hopping, but it's to rearrangement of chemical bonds via vibrations.
We call it structure breakers and structure makers.
Regular?
You could call it, yeah.
One is lithium chloride, for example, is a breaker.
Yeah.
Lithium chloride is a maker.
Right. Okay, so the polymer electrolytes, in a sense, the state of the art is dominated by the perfluorinated sulfonic acids, having equivalent weights down to 1100 to 1000. The membrane thickness is about 25 microns. They are mechanically self-supporting, and they're occasionally mechanically reinforced. And currently, even thinner membranes are under development. The challenges to the polymer electrolytes are water management. They are the operating temperature, but the water is sitting in there, and there is a message that Windows tells me whatsoever. And let's say the operating temperatures, they are a little bit too low, or let's say the comfort zone for the polymer electrolyte operating temperature window is a little bit too low to match the automotive cooling requirements. And the cost, well, the target is of the order of $7.50 per kilowatt, and the real cost is quite a bit higher. Just wondering if there's anything unclear, or if there's since there are some heated debates in the auditorium. Is there anything unclear, or is it just no? If there are questions, please feel free to ask them.
It's just because from what I have read, sometimes mainly, like I said, you have really some hopping from
The mechanism changes depending on, or let's say the preferred mechanism changes depending on the degree of hydration. In the drier state, you've got preferentially the hopping stuff. In the well hydrated state, you got the hopping stuff augmented by the Scrotus type mechanism. However, now being yeah. 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 But let's say being from the practical fuel cell developers end, we typically sustain a highly hydrated situation in the polymer membranes. So we don't care too much about small polar and hopping and stuff like that. We typically try to rely on the faster mechanisms like the Grotus and like the typical ions in motion by, let's say, diffusion way. Yeah.
You said in the previous slide that you need the increased temperature to match. What's the implication?
Well, there's also a heated debate on that. At the moment, the comfort zone for the polymer for the perfluorinated sulfonic acids is of the order of 50 to 60 degrees, and that's a bit on the low end. Although during most of the vehicle operating time, these 50 to 60 degrees are not even reached. However, under full power, one would rather have operating temperatures close to 90 to 95 degrees. Some people are talking about 120 degrees in order to minimize the coolant area in the vehicle. So the higher you drive a fuel cell, the more of the chemical energy of hydrogen is transferred into heat. If you drive fuel cell to higher current densities, you get lower voltage. Automatically, you get more heat. Therefore, you need to remove that heat from the system. And in the case of a fuel cell, as Derek was telling you yesterday, almost 100% of the heat has to be taken out by a coolant loop from the fuel cell stack.
only very little is taken out by the reactant flow, either hydrogen or air. And from that point of view, you would like, in order to access the higher power densities, you would like to be able to raise the operating temperature. Now, the state-of-the-art perfluorinated sulfonic acid membranes, they don't become chemically unstable at 90 or 100 or whatsoever degrees. They just, let's say, change their degree of hydration, and they're losing water pretty fast. And from that point of view, you're increasing the internal resistance at this low humidification. So in order to counteract that, you have to humidify. You have to humidify the air, and then we can't cover that in that kind of in that course of lectures. But humidifying air, the higher the temperature, the more humidity the air can pick up, right? And so the higher the temperature, in order to get a certain degree of humidification, let's say 80% relative humidity, 90 or whatsoever, the more water you have to push in. And this water has to come from somewhere. So you typically carry it over from the cathode exhaust into the cathode inlet. And these, let's say, humidity exchangers, let's call it that way, they're in a sense membrane. That's typically done by membrane diffusion. They are limited in their transport capabilities, so that you can, let's say, only get to a certain dew point. You know the concept of the dew point. It's, let's say, the temperature where it starts raining, and you can't go beyond that. And then at the dew point, you've got, per definition, 100% relative humidity. And as soon as you increase the temperature, let's say the capability of water getting into that hotter and hotter gas, absorbing that hotter and hotter gas, increases exponentially. And so you're pretty soon in a situation where you have very, very low relative humidity of the air going into the fuel cell. And so this is the actual limit of state-of-the-art perfluorinated electrolyte membranes, particularly the ones of the Nafion type. Some of the shorter chain materials, which we are coming across later, they do better in that respect. Yes. Okay, where are we? Currently, we are at the order of about $200 to $500 per square meter, roughly per kilowatt in that respect. And at the moment, it's difficult to tell. But at the moment, it represents maybe 20 or so % of the overall cost. So it's a significant part. However, if we are getting, let's say, closer and closer to the commercial target, the part that the membrane and the catalysts play increase. So there's a challenge on cost reduction in membranes. These figures, cost targets, they are set up by mainly the U.S. Department of Energy. So there will be fuel cell business even at higher cost, but let's say these targets are somehow derived from state-of-the-art vehicle cost and cost share of the propulsion system as compared to the rest of the vehicle. And so you can, let's say, boil that down to cost objectives, and the $7.50 per meter square is, let's say, a result of this boiling down the cost objectives. You can always question that, and we could talk forever and a day about cost targets of individual fuel cell components. So we better leave it for, let's say, tonight during a beer or so. Okay, now at the end of the day, the electrolyte needs to provide conductivity. And in a sense, we would really like to be there. In the polymer membrane fuel cells, we typically are around here. And this has some consequences. If we want to drive a fuel cell to a real high current densities, we need low resistance in the fuel cell. So at a given conductivity, or at the for example, we can reach a certain area resistance by just making the material thinner or thicker, right? So if we, for example, would accept an efficiency loss due to electrolyte resistance in the fuel cell of about 10%, then if we would like to operate at a current density of 1 amp per centimeter square, frankly speaking, today's objectives are closer to 2 amps per centimeter square rather than 1 amp per centimeter square. Then, in any case, we would need an area resistance of about 100 milliohms centimeter square, right? And then we can calculate the thickness of the electrolyte required to meet that area resistance if we, for example, have a certain ionic conductivity in the electrolyte. So if we've got the electrolyte at 100 micron thick, we need conductivity of the electrolyte of the order of 0.1 Siemens per centimeter. If we are able to make an electrolyte 10 micron thick, then it would be a hundredth of a Siemens per centimeter. And if we would be able to make an electrolyte less than 1 micron thick, then we could live with a thousandth of a Siemens per centimeter. Now, in the polymers, we are typically somewhere in between here and there, right? Thickness between 10 and 100 microns. 100 microns today definitely is too thick. State of the art is of the order of 25, going down to 10. The solid oxide people are playing in that region. Meanwhile, 10 to 1 micron electrolyte. So that's a challenge for the polymer folks.
They are using nanofibers.
Well, they're using let's say vapor deposition type electrolytes, very thin ones, which are made by technology thin enough to cover the whole cell. So in a sense, the classes, the perfluorinated, and there are the competitors, basically based on a polyaromatic backbone. Let's say the mother of all perfluorinated polymer electrolytes is Nafion. Well, there's a nomenclature to it. 117, for example. 1 stands for generation 1, 1 for equivalent weight of 1100, and 7 for 7 mils of thickness. So there are other quantities like 112 or 212 or 105 or whatsoever. So you can second guess what's in it if you know that number. In the polyaromatic polymers, there are some advantages. They're not so expensive. The raw materials are quite easily available. They're pretty tough. They have, to a certain extent, low methanol and hydrogen permeability, and they can be easily recycled by conventional methods. However, there are disadvantages. They're very susceptible to radical attack, radicals formed from peroxide, and so we observe fast chemical degradation, and we have a challenge in terms of proton conductivity at low relative humidity. The partially fluorinated ionomers, they do a little bit better, particularly in terms of stability. So fluorine atoms, fluorine substituents have been added at the, let's say, pathological parts of the polymer chain. These are basically multi-plot copolymers. They are quite connected, well connected with hydrophilic ionic channels, and they can form nanophase separated morphology, and can transport protons even under considerably lower humidity. Now, how can we think of these polymer electrolytes? And we can get again in heated structural debates. Now, the oldest model is something like these are connected pores of some 4 nanometers in diameter, connected by channels of about 1 nanometer in diameter. Yet another model is that they are a pore system made from a phase-separated polymer, where the hydrophobic backbone orients towards each other and the hydrophilic front end orients to each other. And in the hydrophilic part, water can absorb and desorb, and you get more or less continuous aqueous phase through the pore system of these perfluorinated sulfonic acids.
So contact angle, I asked the question again. So what is it? Some people said very low, some said not low.
Let's say the concept of a contact angle in these polymers doesn't work. Well,
because it's porous?
No, it's not. It's not because it's porous, but let's say the contact angle. You measure the contact angle at a macroscopic physical quantity. So you can determine contact angle in these polymers. I tend to compare them with acidic nanosponges, right?
Yeah.
And they are made of, let's say, father is PTFE and mother is sulfuric acid.
Doesn't that give the average?
So, in a sense, you will find areas, if you look fine enough,
Yeah.
that are quite hydrophobic, and you will find areas which are quite hydrophilic. And you find a very, very strange behavior of these materials. If you take a piece of these perfluorinated sulfonic acids, dry it in an oven, take it out under ordinary conditions, throw it on a balance in an ordinary climate, maybe not in the desert, or maybe not here, then you will see that the weight increasing and increasing. Since the material is highly hygroscopic, it absorbs water from the atmosphere. Now you do the very same thing. You take this polymer electrolyte, you throw it into water of temperature about 80 degrees, take it out, blot it dry, throw it to the balance. What happens?
Doesn't change?
It loses weight. So the characteristics of water in these polymer electrolytes changes with the degree of hydration. So in the very dry state, the hygroscopic sulfuric acid-like behavior dominates. Then there is a degree of hydration which is in equilibrium with the environment, where you have an average conductivity somehow. And now if you want to go to the very high conductivity, then you will realize that the material loses water faster than if you put next to the material a drop of water to your tabletop. So in that case, in that very highly hydrated case, the characteristic of the hydrophobic backbone starts to be prominent and starts to influence the behavior of the material.
Aluminum ceramic shows the same behavior, but you have to go 400 degrees Celsius.
Yeah.
To hydroxylate the cells, make it orange.
Also, let's do XPS studies to look at the concentration of sulfur on the surface, which will vary from one type to another.
That's right. Okay, so I would just walk very briefly through the different models how people are thinking of. So there is sort of a sandwich model of building blocks and along a chain where the building blocks are somehow twisted and form a continuous pore, or you find these rod-like structures where the hydrophilic and the hydrophobic parts are in a sense orienting towards themselves. Then you find models which change, let's say where the nanostructure changes from dry to almost dispersed and dissolved. So in their working, or you find kind of pore forming arrangements. So let's say from a practical point of view, you could look at these electrolytes. If you don't do elaborate electrolyte science, you can look at these electrolytes as being, let's say, something like nanosponges. You've got to fill them with water in order to make them highly conductive. It's pretty much as sulfuric acid. Pure sulfuric acid and pure water don't conduct ions very well, but mixtures of sulfuric acid and water, they are doing a lot better, and there is an optimum somewhere. And pretty much the same applies to these polymer electrolytes. They need water to conduct protons. However, the optimum will not be reached, otherwise the polymer would already be dispersed in the solvent. Now, we do have many side chains. The mother of all, Nafion 3M, has a 4-chain length, Asahi 3 chains, Solvay, Solexis, and Dow chain length of 2. They are different in their physical properties. They're different in their, let's say, water retention properties. They are different in many ways, but they're, let's say, one class of materials, and they have the same attitude as they want to be well hydrated for, let's say, conducting protons. This is a very old study done by Sawoczynski a long time ago on the conductivity as a function of degree of hydration of the Nafion. And you see, conductivity increases. It increases by, let's say, at least 1 order of magnitude from dry to fully humidified. And the objective of running a fuel cell is to stay as close as possible here, in order to minimize the resistance in the fuel cell. And so, from that point of view, the maximum you can get out of the atmosphere is something like 14 moles of water per sulfonic acid group. The situation where you want to be is of the order of 22 moles of water per sulfonic acid group, and that means that you, as a fuel cell operator, have to make sure that the electrolyte part is very close to that degree of hydration, without simultaneously clogging all the porous structures in the fuel cell. So you have to keep the fuel cell somewhere in between drowning and drying, at the edge. Now, coming to that comfort zone. That comfort zone at about 55 degrees is pretty wide. So you can, in a sense, move along that and still keep the electrolyte in the comfort zone. The higher the temperature, the steeper and the narrower the zone of being right in between flooding and drowning and drying becomes, and the more elaborate you need your operating strategies, temperature-wise, flow-wise, current-wise, in your fuel cell. And from a materials point of view, if you were able to raise that broad comfort zone to higher temperatures, then this would help a lot.
Because there is no size on that polymer for water or if hydroxyl molecule to bond. That's what we don't have.
It's the sulfonic acid. And that's it. Yeah, that's right. And so, from that point of view, you've got pretty nice challenges to make those polymers. However, be aware, even if we would run all the world in fuel cell cars, this material you build will never be so abundant like typical structural polymers like polypropylenes or polyimides or so. It will always be only a few tons per year, since the membranes are so thin and the power density of the fuel cells are so large. Well, let's have a look onto some water distribution. You see here a degree of hydration of about 5 water molecules per sulfonic acid group. 10. You see there is a lot of water going around these sulfonic acid groups, and the higher the degree of hydration, the more the probability that these water clusters merge into each other and become more and more closer to liquid environments. And you can do some polymer dynamic simulations where you can see, let's say, if you look at this part, if you see a temporal evolution, then you see that water somehow bridges from here to there a gap in the overall nanoporous structure of such a polymer. So the effect that I described to you before, like Nafion type polymers pick up water from the atmosphere, achieve higher conductivity, and at a certain point they're losing water to the environment. This is a measurement of conductivity of Nafion under 100% relative humidity in the atmosphere around. And you see, with temperature, conductivity increases. At about 70 degrees, it reaches a plateau. So the conductivity increase, we understand, it's kind of an activated behavior. There's kind of an activation energy behind it. It's also pretty close to, let's say, an exponential increase. Yes? Not by heart. Not by heart. But the interesting thing is, you wouldn't be able to if you do a kinetic analysis, an Arrhenius plot out of it. It will never end in a linear relation, since you have two processes counteracting. One process is increase of conductivity due to increase of temperature, and the second is decrease of conductivity by loss of water. So we started here with a fully hydrated Nafion out of an 80 degrees bath of water, 100% relative humidity. Here the Nafion loses water, and then it drops down at, let's say, the conductivity drops down at about 90 degrees pretty badly. And if you did the experiment backward, it would run on that line, right? And as soon as you take the sample out again, throw it into 80 degrees water, it restores to that point.
It's the indication of physics option.
It is. Right. So what are the consequences of water uptake? That's the swelling of a membrane. And Nafion itself makes a dimensional change of more than 20% in either dimension. So to a certain extent, the swelling behavior is also depending on the manufacturing process. If they are calendared or made by a roll process, we do have an anisotropic swelling. If they are, in a sense, made by a casting process, we find an isotropic swelling. But just think about, you've got a fuel cell, maybe 30 centimeter in length, 10 centimeter in height, and you've got a material that swells about 20% in XY direction. 20% of 10 centimeters are 2 centimeters. So you've got the material would like to be 6 centimeters longer or shorter in one direction and 2 centimeters in the other. That's a lot of strain these materials will have to absorb if they are run in a fuel cell environment. There's a lot of force behind.
And also the issue of lamination is very important.
That's right. Now, what do people against that? Well, some concept is to impregnate these materials into fibers, into nanopore or more microporous membranes, like Gore does. They take their standard their Gore-Tex membranes, the biaxially extended PTFE material, and then they coat the ionomer into the microporous system and mitigate the effects of swelling and translate them mainly into the Z direction, where there is more flexibility. You see here some micrographs of these reinforced membranes. Water balance in the cell. Well, we have water generation here. we have proton transport. With the proton transport, we are transporting water from the anode to the cathode, and we have water diffusion. Typically, since there is a lot more water at the cathode side, it goes into that direction. So we have, in a sense, back and forth traffic of water in the electrolyte membrane. And so we have to live with it, and we have to make best use out of it. And so the overall water balance in the fuel cell is a lot depending on the thickness of the membrane, the transport properties in the membrane, the relative humidity at the anode and the cathode side, and in a sense the transport properties of the gas diffusion layers. So, summarizing that one, water in a PEM fuel cell is required to achieve the high electrolyte conductivity. It's produced at the cathode according to Faraday's law. It must be removed according to its generation, otherwise the fuel cell would drown. You can do that by either condensation or by airflow. Water in a PFC is migrating by electroosmosis from the anode to the cathode, and it's diffusing from the cathode to the anode. And setting the right or wrong operating conditions will push water removal either on the anode or the cathode side, right? And let's say operating condition and material selections are the key to where you find most of your water removal. And let's say most of your statistical operating problems in PEM fuel cell are unwanted water at the anode side, flooding of the anode.
Sorry.
Yeah.
Two questions about the slide before that. Is it so that the hydrogen should always be humidified or not? According to this slide?
Well, not necessarily. As I said, there is traffic back and forth. There is a driving force for water to diffuse to the anode side. Now, if you're talking real thick membranes, let's say the hydrogen side will be dry, mainly, and so it will help to humidify the hydrogen. If you're running real thin membranes, you need to make sure that not too much water is leaving the cell at the hydrogen side. Otherwise, you might get into trouble in removing the water from the hydrogen side. So we're still at a one-dimensional look at the fuel cell. You have to keep in mind that fuel cells have at least two dimensions to worry about. So you can operate a fuel cell on unhumidified hydrogen. That's no problem. It's pretty difficult to operate a fuel cell on unhumidified air.
Sorry, I have a question.
Yeah.
My question. Have you ever drank the water on the cathode side? Water is drinkable.
Well, in small quantities, it's.
I've seen somebody drink.
It's distilled water. It doesn't taste good. And if the fuel cell is really well run in, then you can drink it. Well, if you drink too much distilled water, you will have some problem with your electrolyte.
Nice.
You should put a bit of salt in it. In any case, some of the microstructural differences, or some of the differences in the materials are reflected in the different microstructures. This here shows just a cartoon by Klaus-Dieter Kreuer on the pore structure of a Nafion type polymer membrane and of polyaromatic type polymer membrane. And what you can see is that in the Nafion type polymer membranes, you've got wide channels, you've got interlinked channels, and you've got almost no dead end channels, while you have, let's say, smaller channels, also interlinked, but quite a bit of dead end channels in the hydrocarbon membranes. And this makes a fundamental difference in the way hydrogen and oxygen are diffusing through those membranes. So these hydrocarbon membranes are a lot more blocking to the reactants than the perfluorinated sulfonic acid membranes. Now, where does the reaction take place? basically we are talking about something like a three-phase boundary, where the catalyst and the electrolyte and the current collector are at the very same spot. Well, it looks more like that. We've got the catalyst support and we've got some particles on top of it, and we have them covered with a polymer electrolyte that's about 2 or 3 nanometer layer that's about 2 or 3 nanometers thick. Now that has a consequence. If we would develop an electrolyte, then we would be very proud of if this electrolyte would block hydrogen 100% and oxygen 100%. That would be the perfect electrolyte. Now, making an electrode out of this electrolyte, we have to bring ionic conductivity right close to the catalyst particles. And if we cover the catalyst particles by electrolyte, even if it's only 2 nanometers, and the electrolyte is too blocking for hydrogen and oxygen, we're shutting down our fuel cell, right? And so there are 2 limits to be observed in developing ionomers. One is, it must not be too transparent for hydrogen or oxygen. On the other hand, it must also not be too blocking for either. So block below here is no good, and above there is also no good. Right.
On that picture,
Yeah.
in just before cartoon. So if this is the exchange done by these contact, right?
Right.
Contact. So if this is the contact, why not make it continuous?
Well,
Why we
it's a
are insisting on making
in a
another
sense,
particle?
it's in a sense a cartoon. We can, in a porous structure, we cannot assume that everything is covered homogeneously. In an ideal world, it would be covered homogeneously. And
This is the contact mechanism now,
Yeah.
because if it is on the surface here, I can say this surface is larger than if it is continuous, but
Yeah.
this is a contact mechanism, so you're reducing contact actually here.
in an ideal world, one would cover all these nanoparticles homogeneously. In the real world, you will never find it. If you cover it too much, you will find difficulties. We will see that later. So, question is: are these perfluorinated sulfonic acids useful for the PEM fuel cell? Well, they're chemically almost inert, but somewhat sensitive to radical attack. They're mechanically stable and quite resistant. They make MEA production pretty easy, and handling of MEA is also pretty easy. They have good ionic conductivity, which obviously is depending on temperature and water content. They're tolerant towards complete drying, and they're acceptable with respect to gas separation and reactant transport. However, we observe a decreasing water content with raising temperature, and this changes the conductivity of the membrane, and it requires controlled humidification or drying of the gases, and this limits somehow lifetime.
I took my words back. Still, I guess nanoparticle is good because we're catching on the surface.
Yeah.
You have a little channel, you can tunnel it. So it's a benefit of making nanoparticles is a benefit. Antenna.
You need nanoparticles in the catalyst to have the high surface. You can't work efficiently with macroparticles.
And that's a tunnel with lots of electron tunnels.
So, in a sense, summarizing, we have electrocatalytic processes. They take place in the fuel cell at the surface of a catalyst. We are using heterogeneous catalysts. We are using acid electrolytes typically, and therefore we need noble metal catalysts. The perfluorinated sulfonic acids, they represent the state of the art. They have good mechanical stability, good chemical stability, good ionic conductivity, sufficient solubility and diffusivity of reactants. They have a high degree of water content, which is required for high conductivity, but they are also having a considerable swelling in water, and which can be partially mitigated by membrane reinforcement. They are also somewhat sensitive to radical attack, and they have to be specially prepared to withstand it. Hydrocarbon-based membranes could be a cost-effective alternative. They have lower water transport, but they have less reactant solubility and transport than in the perfluorinated sulfonic acids. And so the concepts we are using to make membrane electrode assemblies out of either perfluorinated sulfonic acids or the hydrocarbon variants, they need to be a little bit different. And that's end of story 1.